interaction-driven insulators in flat band moire superlattices. So Cecile, whenever you want.
Okay, thanks, Maya. Well, first of all, thank you very much for the invitation. I'm very happy to be here. Of course, I'll join everybody in saying that it's super sad that we should be in San Sebastian, but we aren't, at least for most of us. So yeah, I hope to see a lot of you in person soon. So hi, everyone. So today I'd like to talk about insulators in moire superlattices. So as you know, moire materials have become this incredibly versatile platform. And I think one of the things that's super exciting is that we can realize a lot of quantum phases in moire materials in general. And I think Pablo last week talked about many of these phases. Some of them are correlated insulators. Of course, there was also superconductivity at the beginning of this boom of twisted bilayer graphene and other moire materials. But since then, ferromagnetism has been observed, quantum anomalous Hall effect, as well as other phenomena such as nematicity, ferroelectricity, and strange metals. So for today and for this whole series of lecture, I would like to focus on a few of them. So correlated insulators will be at the center of these lectures, and that will include phenomena such as ferromagnetism and the quantum anomalous Hall effect. So a mix of topology, interactions, all of that to see how these interesting insulators can arise in moire materials. So this is the rough outline of the lectures. Today I'll start with a quite progressive introduction on incompressible phases and their filling fractions, and especially those insulating phases that can be found in moire materials that maybe couldn't completely be observed in other types of solids. So this part will be a little bit phenomenological with a little bit of experimental data and quite general, I would say, very, very non-technical. Then I will focus on one specific moire material, which is magic angle twisted bilayer graphene, aligned with its hexagonal boron nitride substrate. And I will distinguish different cases. So for today, we'll only look at integer fillings, and we'll be interested in ferromagnetism and quantized anomalous Hall effect. So the idea is to understand this phenomena from the microscopic point of view. And then later on, so today and tomorrow, we'll move on to fractional fillings and other types of phenomena, such as the fractional quantum Hall effect or symmetry breaking phases. So phases that basically require a fractional filling of the mini bands in twisted bilayer graphene or other moire materials. And finally, if time allows, I'd like to get a little bit more technical with some, by explaining a few numerical signatures of fractional quantum Hall phases, since fractional quantum Hall phases will be the focus on the second lecture. I like to show you some methods of, how do you diagnose those phases when you're doing numerics and you want to know whether you have a ground state that has topological order or not. But yeah, so for today, we'll focus on integer filling for the most part. And as I said, I'm starting with a very progressive overview of incompressible phases and their filling fractions. So this will kind of serve as a something very general that allows me to give a framework to all of my lectures. We're starting with the very basics, which are band insulators. So those are the simplest insulators you could think of. I said we were going to talk about filling fraction a little bit. So here what I mean is that in a band insulator, you have a very simple relationship between the number of electrons and E and the number of unit cells. So here we are on the lattice, there's no magnetic field. And band insulators arise when you have a proportionality between the number of electrons and the number of lattice unit cells. And if you have an extra degree of freedom, like typically you have spin, you'll have bands that are twice degenerate. So you expect band insulators quite simply for an integer which is even. There's a slightly more complicated situation of having an odd filling. So here, depending on the microscopics, you might or might not get an insulator. And if you get one, it can be because spin is polarized, for example, and that will give you a correlated insulator. Now, the next very simple example of an insulator is the quantum Hall effect. And like Jen Cano emphasized in her lectures, in her first lecture, I think, we have a different type of insulator. It's a topological insulator. And here we have also a different relationship. We have the number of electrons now is not tied to number of lattice unit cells, because essentially we are in the continuum. But it's related to the number of flux quanta that go through the system. And here we will find a band insulator in a sense. So we'll have an integer quantum Hall effect as soon as the number of electrons is an integer times the number of flux quanta. So here, I've called this T here, but very often you would call this nu. This is the filling fraction of Landau levels in the quantum Hall effect. And again, you have the degeneracy of spin, even though it's slightly lifted because of the Zeeman effect. So for even integers, you know, the gap is just the cyclotron gap. And for odd integers, well, this is, you also have to include interactions to understand the nature of the gap, but we'll come back to that later. For now, we just need to know that at filling 1, for example, of the lowest Landau level, we have a spin polarized integer quantum Hall effect system. Let's talk a little bit about observables, still in the context of the quantum Hall effect. When you have an incompressible phase, Streda's formula tells you that the whole conductivity in the right units is given by the derivative of the electronic density with respect to the magnetic field. So d rho dB, which I can also write with my notations, d and E number of electrons, d and phi number of flux quanta. So automatically I see from this relationship that I have a quantized Hall conductivity, which is what defines the quantum Hall effect. And so this is an observable, and that's, you know, this corresponds to the Hall plateaus, the very characteristic signature of the quantum Hall effect. You look at the transverse conductivity, the Hall conductivity, and you see that it evolves as these plateaus, an integer times E squared over h, the quantum of conductance. There's another way to look at the Hall conductivity, which is actually from the longitudinal transports, not the transverse transports. And that could be by looking at Landau-Fan diagrams, such as this one. And the idea here is really to use Streda's formula to extract the Hall conductivity. So here, what I'm showing is the longitudinal conductance for different colors. So blue means very small conductivity. So it means you have an incompressible phase. So every time you have an incompressible phase, you can use Streda's formula. And that will give you these lines in the magnetic field versus density plane. And from the slope of these lines, using Strela's formula, you can recover the whole conductivity, which again helps you recover, helps you realize that you do indeed have the quantized value for the whole conductivity. Now I've worked in two very different regimes. First, I had a band insulator with no magnetic field, and then I had a system with a strong magnetic field, and I had two different relationships for NE versus number of unit cells, or NE versus number of flux quanta, but I can very well put them together and generically observe incompressible phases when NE is the sum of S and S, and T and phi. Again, if I remove the magnetic field, I find the first relationship. On the other hand, if I'm in the quantum Hall regime, which is mostly continuum, the first part is negligible compared to the second term. To show that this approximation was indeed justified in the quantum Hall regime, I can just compute the typical value of the magnetic length for a typical magnetic field. Let's say 10 Tesla, which is already a very decent field. Then the magnetic length will be equals to 8 nanometer, which is much, much larger than the lattice constant for a typical lattice. For example, if you take the graphene, if you take single layer graphene, and you wanted to have one flux quantum in every hexagon, you'd need a magnetic field of around 40,000 Tesla to reach this sort of order of magnitude, which is completely crazy and unfeasible, of course. And now, of course, you know where I'm getting at, which is, to me, maybe the first advantage, or the first things that makes Moiré systems very interesting, is to change the length scale. So by working with Moiré superlattices, a length of around 10 nanometer is something that is very doable. Now you can indeed have a lattice, superlattice actually, with a lattice constant that is of this order of magnitude. So you can have the order of magnitude of the magnetic length roughly equal to the lattice constant. So here I'm showing some, again, some experimental data where this phenomenon was observed and explored. So the data here comes from graphene aligned with a substrate of hexagonal boron nitride. And so both graphene and HBN are hexagonal, and they have almost the same lattice constant, but not quite. There's a very small 1.8% mismatch between the two lattice constants. And when you align those two lattices, this creates the Moiré superlattice with the largest possible unit cell. And it will be around, or maybe a little bit more than 10 nanometers. So that will allow you to explore new things compared to your purely quantum Hall regime, and more specifically, it will allow you to explore the regime S non-zero in this Diophantine equation here. So if I'm looking a little bit closer at the data, so again, this is longitudinal conductance. So basically, I want to look at all the at the very at the darker colors here, which corresponds to smaller longitudinal conductance, because that means I have an incompressible phase, and I will see lines in that case in the B versus electronic density plane. So here, the unit is the gate tension, which is what allows you to actually change that density in the sample. So I have here my usual Landau levels, let's say, all basically those lines that go through that cross the y-axis at 0 field. This is just the typical common Hall effect, but you see, for example, around here or around there, that there are other lines, for example, this one or that one, that correspond to a non-zero S. So you really explore this, you start exploring the full possibilities of the combination of lattice and magnetic field. And I didn't say it, but you've probably noticed that there were other lines that didn't have a linear slope. They have a fractional slope, and I haven't. So these correspond to fractional quantum Hall states. I haven't talked about this yet, but I'll come to that later. So exploring all those possibilities means that you're exploring the Hofstadter butterfly that probably you know or have heard about. So basically, the idea is that when you have a magnetic field on the lattice, you can explore that with a tight binding model by doing a Pyle substitution, meaning that you'll take into account the effects of the magnetic field by replacing those simple Hoping terms by a Hoping terms times a phase. And the phase is given by the integral of the vector potential along that path taken for the Hoping. So this is what Hofstadter realized is that then you could write on a model like this, and well, you can write it down in any lattice. The simplest is the square lattice, but you can do a triangular or honeycomb and so on. And that will, if you solve the Hamiltonian in that case, or the Harper's equation, this will give you a spectrum which has a self-similar structure. It is fractal. And each gap within the spectrum, so the way to look at this is to fix phi, the flux quantum, and this is the y-axis corresponds to the energy. Each gap corresponds to an incompressible phase. So if you are at small flux, you'll recover your typical Landau levels, but as you go more towards the phi equals to phi naught, the unit of flux quantum, well, then you have a very different physics. So this is the first point that I wanted to emphasize for this first lecture, is that, well, Moiré superlattices, they allow you to first explore the Hofstadter butterfly in the regime phi close to phi naught or half phi naught. So they allow you to really go into this very interesting physics, which combines lattices and magnetic fields. And finally, so this is moving on to a different aspect. You can consider fractional fillings and fractional conductivity. So here I'm continuing my overview of incompressible phases, if you like. So again, using that Diophantine equation, instead of having S and T be integers, I can have rational fractions. And okay, maybe I should be very clear about this. I'm not saying that there's an insulator for every S and T integer or fraction. I'm saying that there can be one. That doesn't have to be. That will depend on the microscopics of the system. Okay, so what's quite cool is you can, again, thanks to this enlarged unit cell, allowed by Moiré superlattices, you can explore all different types of combinations of S and T being non-zero and also being fractional or integer. So here I am showing you some data that comes from Andrea Young's lab. And here it is a bilayer, Bernal stacked bilayer graphene aligned with the substrate of hexagonal boron nitride. So the origin of the Moiré superlattice is again, like the previous data I showed, is again due to the lattice constant mismatch between graphene and HBN. And again, this is data in the B, magnetic field versus electronic density plane. Here, this is not actually conductance data, but capacitance. This is a different way of probing whether your system is compressible or not. But again, you have these different lines, which have been analyzed by the authors in this second diagram here. And they can identify a lot of different combinations of S and T being zero, non-zero, fractional, or integer. So if S is, yes, so T, again, according to the Strata formula, as soon as you have an incompressible phase, T basically gives you the whole conductivity. So if T is fractional, T equals to P over Q, then you have a fractional conductivity. And then if S is zero, basically no lattice effect, no super lattice effect, we call that just fractional quantum Hall effect. But if it's non-zero, that means that you've obtained your you obtain your fractional quantum Hall effect by filling a Chan 1 band that comes from the super lattice, and we'll call that a fractional Chan insulator. Because this is, there's no way to explain the phenomenon without the reasoning, including the superlattice. Another option is to have a fractional filling. And in that case, you don't necessarily have a fractional conductivity. You could also have a symmetry broken phase that has an integer conductivity. So that corresponds to the pink line in this diagram that the authors have called symmetry broken Chan insulators. So you still have probably a non-zero Hall conductivity. T is non-zero, but not fractional, and a fractional filling. So you can, well, the insulator then comes from breaking a spatial symmetry by forming a charge density wave. But I'll talk more about this in the Solomon lecture. Okay, so that's pretty much all I wanted to say for my overview. I think I've talked about a few different phases, all insulating, and all fit within that framework of having a number of electrons that's equal to S times the number of unit cell and plus T times the number of flux quanta. And the first message that I've emphasized in that overview is that length scale matters here. And Moiré superlattices allow you to have a lattice constant that is of the same order of magnitude as that of the magnetic field. So that's the first thing. And it's already super important and really new to be able to to explore all the aspects of this Hofstadter butterfly physics. But as we now know since a few years, it also allows you to do many other things. Moiré can allow you to do many other things. One of them is to have topology without any magnetic field. So I think this is a theme that was explored quite a bit in Andrei Bernevik's lectures. And here I will be mostly interested in the case where you can have a non-zero Chan number, but there are other things such as fragile topology. And finally, Moiré systems allow you to have flat bands thanks to magic angles, for example. So it allows you to explore strong correlations. So now I am moving on. And instead of exploring this first aspect, I'll be exploring the interplay of this topology and flat bands physics. And I'm going to do it by focusing on one particular Moiré system, which is magic angle twisted bibliography aligned with hexagonal boron nitride. So I'll be talking first about band properties. So for this part, there's going to be a bit of overlap with Andrei and Oscar's lectures from last week, but this will be quite short, and I will quickly go through things that are new in principle compared to these lectures. So right now, I'm setting this in the context of band properties, so I'm only considering single particle properties for the time being. Okay, so twisted barrier graphene. So I think by now you've probably heard this many times, but let me go through it one more time quickly. So in monolayer graphene, you have a hexagonal lattice with A and B sublattices. And if you diagonalize the Hamiltonian, you will obtain this structure where you have Dirac cones at every corner of the Brillouin zone. And you have two inequivalent corners, which are called valleys, K and K prime. You also have two spins, so that will give you a four-fold degeneracy. Now, twisted barrier graphene consists in stacking two layers of graphene on top of one another and having a controlled angular mismatch between those two layers. That means that I have, in real space, a much larger lattice constant, and in momentum space, a much smaller Brillouin zone. I can, so if I'm focusing on that, I can see that when the angle theta, the rotation angle theta is small, the two K prime coming from top and bottom layer are next to one another. They will form one mini band. Well, more than one, but they will form one mini Brillouin zone, let's say. And then the two K coming from top and bottom layers will form the other mini Brillouin zone. And there's no, well, the scattering between K and K prime valleys is exponentially suppressed. So we can neglect it and consider the two valleys independently. Now, you know, as you have your superlattice potential, that means that you are folding all these, well, you are folding the original bands of graphene several times. So that will create thousands of mini bands. And of those bands, we want to focus on the conduction and valence bands. So thanks to the scattering between, well, thanks to the tunneling between the top and bottom layers, there are gaps that are opened, and conduction and valence bands are separated by a gap from lower and higher bands. So you know the usual story that as you go to very small angle, there's a, well, you flatten the band very much until you reach a magic angle of around 1.1 degree. And then if you keep going down, they will, well, the bandwidth will start growing again, start increasing again. So, so we'll stop at the first magic angle. And okay, so this is now where the story now differs slightly from the regular magic angle twisted barrier graphene, is that we're going to consider the magic angle twisted barrier graphene in the case where it is aligned with its hexagonal boron nitride substrate. So now I'm going to slow down again to treat this part. So let me describe the model that we are using to describe the situation. So as is the case for magic angle twisted barrier graphene, we neglect spin-orbit coupling. It's extremely small. Intervalley coupling is also neglected in this model because it's exponentially suppressed. And what we'll do is we start from the Bistreser-McDonald model. Again, this is just a reminder from what you did last week. So we can separate valley K plus and valley K minus, you know, however you want to call them, but the valleys corresponding to, well, valley plus correspond to one chirality, and valley K minus is the time reversal partner of that valley. So we can write down the Bistritzer-McDonald model in this valley, in this one valley. So here I'm writing it down in K space, and we have spinors here in corresponding to the top and bottom layers, and each of these psi is itself a spinor in sublattice space. So it has two components, an A component and B component. So if really I wanted to expand everything, I would have a 4 spinor here. And so here we see, so this is just a reminder of the fact that we have Dirac cones. Well, we have the Dirac particles for both the top and bottom layer, and the chirality for the top and bottom layers are the same. So this is the diagonal part of the Hamiltonian. We have sigma matrices, Pauli matrices acting in the sublattice space here. And we have the second part, which is the Murray scattering or the coupling between the two layers, if you prefer. And this coupling occurs for wave vectors that are reciprocal lattice vectors of the Murray superlattice. So they are called GJ in this case, in this language. And TJs are terms that I'm not going to repeat here what they are. This was quite well described in both Andre's and Oscar's first lectures last week. Okay, so this is just and I didn't mention the fact that so you could add, typically since we have rotated layers, it would make sense to add a rotation for to rotate one of these Dirac dispersions. You can, in fact, neglect it again, as was explained last week. Now, to this plain Bistritzer-McDonald model, I'm going to add a term which breaks C2T symmetry. And that terms come from the alignment with the hexagonal boron nitride substrates. It's maybe it gets a bit confusing here because I already talked about aligning graphene with an hexagonal boron nitride substrate earlier, and the effect I talked about was to create a Moiré superlattice. Now I'm talking about creating a mass term. So both of these effects exist, and depending on the context, they might be, more or less important. This is, I want to focus on that aspect, the fact that you are breaking C2T symmetry. So this is just due to the fact that boron nitride, well, this is it has two types of atoms. So it will just act differently on A and B sides when it's well aligned. Twisted bilayer graphene, similarly to single layer graphene, actually, its Dirac cones are protected by this C2T symmetry. So by breaking the sublattice symmetry, you break the C2Z symmetry, which in terms, in the end, breaks this product of symmetries. So effectively, this is like adding this sigma Z term in the Hamiltonian. And note that I've only added it to one layer and not to the other, because typically only one of the graphene layers is aligned with the substrate for practical reasons. But this is enough to open a gap in all of the Dirac cones. So this the amplitude of this gap is around 15
this mass is around 15 milli-electron volts. This is a gap that was experimentally observed in these experiments and later analyzed theoretically. This is a little bit subtle because in principle, since the two lattice constants, the one of HBN and the one of graphene are not exactly the same, you should basically add a plus delta AB sigma Z on a one zone of the superlattice, and then half a paired further, you should have a minus delta AB sigma Z. But it turns out that effectively, this is not what happens. Effectively, it's enough to just add this one uniform term on the whole lattice. All right. So you've opened this gap. So you started from this condition and valence band that were touching each other through Dirac cones. You've added this mass term in one of the graphene layers, which has opened a gap thanks to breaking sublattice symmetry. Now this means, because you have a gap, you have a well-defined Chen number in each of the bands. Yes?
Cecile, you have a question from
Sure.
Martin Gutierrez. This also breaks the particle-hole symmetry that was conserved by rotating the sigmas.
Yes. For me, it doesn't really matter that particle-hole symmetry is not conserved. So yes, it's broken.
Okay, thanks.
All right. Yeah, so you have now a well-defined Chen number for each of these bands. And because you started from a model where in a given valley, you had the same chirality for each Dirac node, adding this mass will actually create a non-zero Chen number in each of the bands. So, this is summarized in this picture where if you focus on valley minus, for example, you may have a Chen 1 conduction band and a Chen -1 valence band. That's identical for both spins. And in valley plus, the conduction band, on the other hand, will be -1, and the valence band will be 1, in accordance with the fact that valley minus and valley plus are time reversal partners of one another. So if I focus just on the conduction band, schematically, I have these 4 bands that are almost flat because I'm at magic angle, and that have these different Chen numbers depending on the valley, and additionally I have that spin degeneracy. Okay, so this was the overview of the band structure properties of magic angle twisted barrier graphene aligned with hexagonal boron nitride. Now I'm adding another element, which is interactions. And this is where we start observing emergent ferromagnetism, as I'll explain now. So let me start with a few experimental facts. Magic angle twisted barrier graphene aligned with HBN has been realized before. And this is what is seen in various experiments. So first of all, there's a hysteresis of the whole conductivity of magnetotransport in general. And this hysteresis indicates an emergent orbital magnetism. So this data is from David Goldhaber-Gordon's group. And this was the first time that this hysteresis, this emergent orbital magnetism was found, and it was found for filling 3, meaning that in mean field this would correspond to in the conduction band filling those 3 bands out of 4. And subsequently, a quantized anomalous Hall effect was also found.
So note here that in the first experiment, the whole resistivity is quite large, 6 kilo ohm, but that's still smaller than the von Klitzing constant, which is about 5 times larger, a little less than that. So subsequently, quantized anomalous Hall effect was also observed. So here again, there's a hysteresis of the Hall resistivity. And maybe I should explain that the hysteresis comes from the fact that as you increase magnetic field, if you have a very large magnetic field in one direction, you're going to fully polarize your system because the magnetic field couples to the Berry curvature basically in your system. And that's going to value polarize the system entirely. And as you decrease the magnetic field going that way, you stay on the plateau of Hall conductivity because you remain in that polarized state, and you're even at you're still quantized at zero field. So you do indeed have a quantized anomalous Hall effect. There's no more magnetic field. It's a spontaneous polarization, spontaneous time reversal symmetry breaking. And as you go down to very negative field, or you invert the polarization, like in a magnet. Yeah, it's probably important to specify the fact that previously quantized anomalous Hall effect had been observed, but in a very different setting. So this is an observation that dates back to, I think, around 2013 or so. And then the material was very different. What they did is they took some thin films of topological insulators. So the topology was coming from spin orbit coupling in those materials, and then they doped them with transition metals, so impurities that explicitly break time reversal symmetry. Here, here the origin of the time reversal symmetry breaking is very different. There's no doping. It's spontaneous, and it's a material with only only carbon and Vn atoms. So let's, after this phenomenology, let's go into some microscopics. So this is a phenomenon that's often called flat band ferromagnetism, and it can be linked to Hund's rule in atomic physics. So Hund's rule tells you that when you have atomic orbitals that are degenerate, it's energetically more favorable to fully fill one level with electrons of the same spin rather than having electrons with opposite spins. So it's basically the solid state equivalent of this rule that is observed in magic angle twisted baryographine, and which shows up through a valiant spin polarization at integer band filling. Well, at least that's what you expect from Hund's rule. And to explore the physical arguments, we can start by thinking of a trivial band, which is not the case here, but there are other twisted or other Moiré materials where this happens, where the band is trivial. So it doesn't fully require the topology in the form of a Chern number. So if you have a trivial band, then you can write down a lattice model through some Wannier orbitals that are exponentially localized, and that could just correspond to that one band. Then you can project the Coulomb interaction onto this band, And that will give you, you will get among the different terms that you'll get a, let's say, Hubbard-U interaction. So you'll get a repulsion between electrons that doesn't depend on spin, but you'll also get an change integral, which favors the maximally polarized states. Yeah, so maybe I should also say that this is something that comes from the fact that the overall wave function has to be antisymmetric. So you can think about it if you just have two sides. You can think about it in terms of minimizing the Coulomb interaction. To do that, it makes sense to have wave functions that are antisymmetric in their spatial parts, and to keep the antisymmetry of the overall wave function, then the spin part must be symmetric, so ferromagnetic. But away from that context of the trivial band, you can also think of the case of Landau level ferromagnetism. So this is what I was mentioning in the very beginning of the lecture. When you have Landau levels, you have a spin degree of freedom. And if you consider the case with a filling fraction 1, you completely feel the lowest Landau level, but just corresponding to just one spin. Since you have a Zeeman effect, it's you could naively think that the fact that you have an insulator in this case, the gap comes from this Zeeman effect, but it's really not the case because the Zeeman effect is very small in energy. So maybe around 0.3 times the magnetic field in Kelvin. Whereas if you consider the effect of exchange in this system, which is roughly of the order of magnitude of the Coulomb interaction, so that's why I'm calculating E square over epsilon LB here, it's going to be of order around 5 times square root of B, also in Kelvin. So for the magnetic fields that are accessible, this second exchange term is always much larger and is really what sets the value of the transport gap in the integer quantum Hall effect with an odd filling. All right. Good. So these were, okay, so I've given some physical sort of intuitive arguments why you should find ferromagnetism in the flat band limit when you have an integer filling. So these are extremely generic. They don't depend on, there's not really anything moire about this except for the fact that you have a very flat band. So that's what allows you to have strong interactions and to have a flat band. I'm going to stay very generic here, but give some slightly more analytic arguments for ferromagnetism. And that requires me to project the Hamiltonian onto the active band. So here, let's say the conduction bands. For this approximation to be valid, you would need the bandwidth to be much smaller than the typical interaction strengths, and which itself should be much smaller than the gap, both below and above the conduction band. It's not necessarily the case, and rather probably not the case in twisted bibliography, but let me still go through the argument because it's interesting, and then we can check how robust it is later on. So here I've written down the projected Hamiltonian. It's we're doing a projection onto a turn band, so it's much easier to do it in momentum space. So V of Q is, well, it's your favorite interaction, and typically you would need you would use a Coulomb interaction, and probably maybe you can take into account the effect of screening in it. But okay, so here this is very generic as long as it is a repulsive interaction. Then rho Q with a little tilde. So the little tilde means that we have done the projection onto the conduction band. And this is something we see here through this form factor, which appears here as the overlap between two wave functions. So I'm showing here the projected density operator for just one Wally and one spin. This is what the tau here means. And so in this form, this is where, well, basically all the, well, the topology and the Berry curvature and all these sort of things, that's where it's hiding when you do the projection. The overall projected density operator corresponds to the sum of all spin and valleys. So yeah, so an argument why there should be ferromagnetism at integer filling in the flat band limit. So the first very important point is that the projected Hamiltonian is positive semi-definite. And you can see it if you realize that rho of minus Q is actually equal to rho Q dagger. So when you do an operator times this operator dagger, this is positive semi-definite. V of Q is positive because we have a repulsive interaction. So this is a sum, H is a sum of positive semi-definite operators, meaning that all the eigenvalues, the whole spectrum of H is going to be positive or zero. The second argument is that if you take a fully polarized wave function at integer filling, so let's say I'm using filling 3, like in the experiments, then this wave function satisfies, you know, if you rho Q psi polarized equal to 0. If you apply the density, the projected density operator onto it, it'll be 0, which means that psi is an eigenstate of this Hamiltonian with eigenvalue 0. So it has to be a ground state. So it doesn't have to be the only ground state, but it is a ground state. Okay, and I'm now running out of time. Let me just mention what happens if you go beyond the exact flat band limit and allow a little bit of bandwidth to be non-zero. So now you know you need to go to a numerical approach. You can do Hartree-Fock. And basically, you will walk within the variational space of Slater determinant wave functions, and that will, you know, show you that the fully polarized wave function is the ground state up until some non-zero finite bandwidth. And if you want to go beyond that approach, you can do exact normalization. And add a little bit of dispersion, either something realistic or here I wrote down something very artificial for the dispersion, but I think the idea is just that you have an interaction term, which is Coulomb interaction projected onto the conduction band, and you add just a kinetic energy term, and you see, you just check whether the fully spin and valley polarized states is the ground state of the system or not. And you know, doing that, you obtain that there's so here, this is a kind of generic result with a lot of different Murray systems, but if you look at twisted barrier in a line with hexagonal boron nitride, it's the purple curve. So you get about 15 to 20% of U for the bandwidth before you do not have a fully polarized insulator anymore. Okay, so I think I'm running out of time. So I will stop here with all the consideration on integer filling insulators in the Murray superlattices. Tomorrow and the next day we'll consider fractional quantum Hall state. I'm happy to go back and give more details about the integer filling case if there are questions. I'm happy to talk about them tomorrow or to answer questions now.
Okay. Thank you, Cecile, for this very nice talk. Are there any questions? I have a question myself. If you use Hartree fog to solve the bands of a Murray lattice, the exchange potential is the same as in a non-Murray lattice?
Well, no, I mean, I'm really not a specialist of that, but I would assume it really, the exchange depends on the whole band structure, right? So I think that would be quite different.
Okay. There are two questions. Okay, from Mikel Garcia, is the interaction really much stronger than the bandwidth in TBG, or are they in the same order?
Yeah, I mean, in principle, I think they are of the same order of magnitude. So yeah, it's very reasonable to question that assumption that we're in the flat band limit. But I think that's exactly why we do numerics, is that so that we can check the effect of a small bandwidth. So maybe here it's also maybe why we do observe some correlated insulators at some fillings and not other integer fillings. For example, in this case, I think for MATBG aligned with HBN, I think there's only this churn insulator is only observed at filling 3 and not at filling 1, for example. So there could be, there are lots of macroscopic ingredients, including the bandwidths that can change sample to sample and even within the same sample from one filling to another. So, it could be an explanation.
Okay, from an anonymous attendee, where is the ferromagnetism localized in the TBG?
Where is it localized? I'm not sure I completely understand. So the idea is that you have it's a valley polarization, basically. So so the system, within, maybe it's this, I can show you this picture again. It's this mean field picture where you have a conduction band that's essentially a narrow band with a fourfold degree of freedom for spin and valley. And
the same person says in real space, sorry.
In real space. I mean, are you asking about the...
I guess he asked or she asked about the atomic site, for example.
I think I can answer some of this in the next talk.
Okay. Well, then maybe this is probably better that I'll let you.
Okay. No, there is one last question. In this projected model you gave, comma, you only consider intraband pairing, right? But with a flat band and approximate particle Hall symmetry, you could also pair particles of different bands. Given that the gap is small, could you?
Okay, I'm not sure I
You
was able to follow. Can I read it somewhere?
Yeah, it's in the
Okay,
question and
yes.
answer.
Intraband pairing, yes. Yes. Yeah, so there is, so is that like, basically, I guess that's a question about projecting the interaction onto the active bands. And I mean, there's an effect from the remote bands, which will renormalize the bandwidths. That's for sure. I don't know if it's the question. Yeah. So yeah, I think that's what I can say here. Maybe I should emphasize that this approach doesn't really try to be super realistic in terms of taking into account all the effects and the interaction with other bands and so on, but rather try to ask in a generic way. We know that interaction with higher bands is going to renormalize the bandwidth. So, no matter where that bandwidth is coming from, is the state stable or not? I think that's the generic answer.
Okay. I think that's all. So thank you very much, Cecile, for your talk, and I see you tomorrow.
Thanks. See you tomorrow.
Bye. All right, so our next speaker is Professor Ephemios Kasiras from Harvard University.
Can I share my screen now?
Yes.
Okay, is that okay?
Yes, perfect.
Okay, great. Thank you very much, and thank you for including me in this workshop. I also wish I could be in San Sebastian or Donostia. I was there just before the pandemic started in January of 2020 for another event, and it really was wonderful, and I wish I could be there.
Yeah, I mean, there is a promise that we will invite everybody who accepted to give the talk online in person when we can.
Thank you. That's very kind of you.
And this has been recorded, so you can use it on trial.
Okay, because I certainly enjoyed that visit tremendously. It really is a wonderful place. So it's very nice to be part of this workshop. And let me start with a brief outline of the two lectures that I will give. The first lecture today will consist of a short review of the basics, both a little bit of experiment and theory. And I will talk about what it takes to create an accurate description of the single particle picture, mostly related to twisted bilayer graphene, TBLG for short, but also we have done similar work in other systems, and I'll briefly mention that, and try to make connections to the correlated electron picture. So in this sense, this lecture is complementary to many of the things that you just heard from Cecile. And in fact, I think I can answer some of the questions that were brought up at the end, because we do have the ability to create an accurate description of the single particle picture of the system, which addresses some of these questions. By the way, can you see the cursor when I move it around?
Yes.
Okay, thank you. And the second lecture tomorrow, which will be given together with my student, Zoe Zhu, will be concentrated on the twisted tri-layer TLG graphene, discussing both atomic relaxation and electronic states related to the system. And this turns out to be a really incredibly rich system for doing this type of physics of correlated electrons in moire patterns. and it gives a much greater flexibility than the twisted bilayer graphene, and has a lot of holds a lot of promise for truly exciting and interesting physics. So Zoe, Zhu, and I will devote the whole lecture on this system tomorrow. Okay, so a little bit of background information. I'm sure you're all familiar with this, but just to pay tribute to the accomplishments of our wonderful experimental colleagues who made all this possible, all this field possible by putting together bilayers of different layered systems with a small twist angle between the layers. And here's very briefly how they do it. They start with a single layer, graphene, for example, stick something else to it and tear apart half of the layer. And now they know exactly the relative orientation of the two halves. And then they put the one half on top of the second half to create the precisely controlled twist between the two layers. So these are experiments that were pioneered by Philip Kim at Harvard, Pablo Jarrillo Herrero at MIT, and many other groups. And then the whole thing is sandwiched between the top and bottom hexagonal boron nitride layers to create a device. So that's a very brief overview of the experimental technique, and it really is wonderful and has made this whole field possible. And these are the kinds of pictures that you see from experiment. So this is a dark field imaging scanning transmission electron microscopy picture from the Philip Kim group. And it's a twisted bilayer graphene at about 0.1 to 0.2 degrees twist. And you see these really very regular and very large scale beautiful patterns of different regions. So where do the patterns come from? Why are they so sharp? What do they imply for electronic behavior? A lot of progress has been made in answering these questions, and we'll be addressing some of these from the single particle picture. So again, a very brief overview of the physics of graphene, the honeycomb lattice, and a pz orbital attached to every site. And the very interesting thing about graphene is that near the Fermi level, the dispersion of the energy levels is linear in momentum. So these are massless particles. Here's the hexagonal Brillouin zone and the Dirac cones associated with each corner of the Brillouin zone, the K points showing the linear dispersion behavior. But what's more interesting is that the linear dispersion relationship is valid only for a narrow range of energies near the Fermi level, near the charge neutrality point, as it's called for a neutral system before being doped. And in fact, if you look at the density of states, so the horizontal axis now is density of states and the vertical is energy. So here is the Fermi level for the neutral system, the charge neutrality point. And this is the linear dispersion relationship, the density of states produced by the linear dispersion relationship. But if you go away from it, you see that the density of states rises sharply. At the Fermi level, the density of states is 0. And that's one of the reasons that graphene has not been used in other types of electronic devices like semiconductors and other standard device configurations. It has 0 density of states at the Fermi level. So it's neither a metal nor a semiconductor. That's why it's referred to as a semi-metal. The interesting thing is that farther away from the Fermi level, you do see very flat bands. So here are the flat bands in single layer graphene. And early on, many years ago, it was hypothesized that if you can access these flat bands, these Van Hove singularities of the density of states, you could get very interesting behavior in graphene. And it was even hypothesized that graphene could become a a superconductor if you could access these states. The problem is that these states are many electron volts, 3 electron volts or so far from the Fermi level. So it's very difficult to access these states in a controllable fashion. Okay. So that's where the twisted bilayer graphene came into play because it made this, it changed this picture and made density of states non-zero near the Fermi level possible. So a little bit about the actual atomic pattern. So this is what you see when you create a twisted bilayer graphene. So you see two layers now on top of each other, and there are regions labeled AA, where the two layers are exactly on top of each other. So you only see one set of atoms or one honeycomb lattice. There are other regions where the two layers are offset. So you see all the atoms on the top layer and half of the atoms on the bottom layer. So that's the standard stacking of layers, of two successive layers in graphite. And this is the low energy configuration. So the system would like to be in this structure and avoid this structure. This is a high energy configuration as far as atomic structure is concerned. And of course, these regions, there are two types of these stacking regions. They're called BA or AB. They're equivalent by a rotation of 60 degrees or 180 degrees. And they're separated by these blue lines, which are domain walls. So that's what you get in terms of atomic structure. And this is the standard picture in reciprocal space, where the large colored hexagons, the red and the blue, come from the two different layers. So these are the K points, the corners of the original Brillouin zones, where you have the Dirac cones, and the small black hexagon corresponds to the supercell produced by the stacking. So let me see. Okay. Now, this is where the Dirac cones appear in terms of the single layers, and of course these single layers now are combined, and there's a Dirac cone at each corner from the different layers. So there's a Dirac cone from the blue layer here, and the Dirac cone from the red layer here. This is the black supercell Brillouin zone, the small hexagon. And of course, these Dirac cones intersect, and here are the two Dirac cones, blue and red, that intersect. And at the intersection points, you get a splitting of the energy levels. And this is what produces these green bands, the bands that correspond to the bilayer. And this is, of course, the very beautiful qualitative picture that was proposed first and described in some detail by the seminal paper, the landmark paper by Bistreitzer and MacDonald. This introduces now two energy scales. There's an energy scale here which has to do with the splitting of, the splitting in energy of where the Dirac cones intersect, and this is entirely determined, it's set by the Moiré pattern. The length scale sets this energy scale. There's another energy scale which has to do with interlayer hybridization, and this is the interaction between the layers. And this interaction is what splits the degeneracies here to produce these bands. And because of the splitting, there's also a renormalization of the Fermi velocity near the K points. So this is the basic physics introduced in reciprocal space, in K space, by the twisted bilayers. And here's the density of states, again, a really crucial feature of the system. So the green lines now, the green density of states comes from the green bands, and the dashed line is the original straight line from the single layer graphene. There's of course two of those, and those are very different. The scale of this is very different, and you see now a large density of states produced by these flat bands. And indeed, this picture was confirmed early on. So this is a set of experiments by the group of Pablo Jarillo Herrero. And what you see here on the horizontal axis is the doping. And on the vertical axis is the diagonal conductivity. This is a measure of the density of states. So you can think of this picture as exactly measuring essentially the density of states on the vertical axis as a function of position on of the energy, which is also related to the doping. So indeed, you see these two big humps here corresponding to the density of states of the flat bands. And these are separated by other bands by these narrow gaps. This is at zero magnetic field. If you turn on the magnetic field, so this is the magnetic field, and this is the doping on the horizontal axis, and you see these, you can identify these different lines, and these different lines are correspond to the Landau levels that Cecile described in her talk. So I'm not going to go into detail in any of this, but this is exactly the picture that would be expected from the simple physics model, and it's verified by experiment. Notice that the angle here is 1.8 degrees. Okay, so this is significant, and I'll come back to this. And this is verified by detailed single particle picture calculations. So this is the band structure according to the tight binding Hamiltonian. And if you take cross sections of this band structure that corresponds to constant energy, you get these constant energy contours, and these give the degeneracies and fully explain the Landau levels that are measured at finite magnetic field. Okay, now the big surprise came with this set of experiments in 2018 by Pablo Jarillo Herrero's group. And what you see here again is the horizontal axis is doping. So you can think of this as moving the Fermi level on the energy axis. And the vertical axis is the conductance, which is again a measure of the density of states. And again, you see these density of states that I was mentioning earlier, separated by large gaps from other states, but you also see mini gaps. So there's a mini gap here and another mini gap here. And if you blow up just this region, and this is again the horizontal axis, the same axis, the doping, the carrier density, but the vertical axis now is temperature, and this is a phase diagram. And for this temperature range, you see a superconductor and another superconductor here. This is a mode insulator. Here you see a metal, and so on. And the superconducting behavior was a surprise, and the mini gaps also were a big surprise. And these cannot be accounted by the single particle picture. Again, this picture is very interesting, but what I want to point out is that the superconductivity is observed at different values of the twist angle. So this value of the twist angle is 1.16 degrees. This value is 1.05 degrees. And again, you see a superconductor, but slightly different phase diagram. And this is important because it tells you that there's a range of magic angles, not a unique magic angle. And I'll come back to this in a second. So as I said earlier, the single particle picture cannot account for the mini gaps. So this is a very simple schematic, a single band, full filling, a single band at half filling. There's no band gap. Instead, you need a more elaborate model. So this could be a single particle model. Instead, you need the on-site, which includes only hopping between sites. So in addition to hopping between sites, you need on-site repulsion or more elaborate models. So this is a many particle picture, which can produce this kind of splitting of the bands due to correlated electron behavior, and then you can have a half-filled band. And this is exactly the kind of level of description of the system that the previous talk was talking about. The question is, how can we build a picture using the single particle information of a many-body description? And in order to do that, we need to figure out what are the single particle levels responsible. So this is a early attempt to try to address this question by looking at Brocchian symmetry effects. So looking at the kind of symmetries that the system has, and then start breaking some of these symmetries and see what kind of bands you produce. So this is work by Sandhill and Ashwin Vishwanath and their students and collaborators a few years ago. This was very instructive and very interesting by breaking different types of symmetries to see what kind of bands you could produce. But the overall effect of this kind of study was that you need very complicated wave functions at the single particle level, which is captured nicely by this schematic picture from physics world, to unravel, to understand what the single particle states are that can produce this kind of band structure. And early on, it was realized that very simple bands cannot account for this kind of symmetries that the system requires in order to produce this description. So we have been working very hard to produce a very accurate description of twisted bilayers, in general of incommensurate layers, because if you put two layers on top of each other at an arbitrary angle, you have an incommensurate system. Once you have an incommensurate system, the momentum is not a good quantum number anymore. So the question is how to describe the system. And one very efficient way that we have found is to use what we call configuration space. So this is shown here schematically. So these are two real space lattices. Blue and red are again the positions of atoms in the two lattices, and you see the different local configurations. So the dashed black lines outline the Moire supercell, and you see different types of local configurations here. So here are blow-ups of these local configurations. So if you refer everything back to one of the lattices, let's say the red lattice, then you see different positions of the second lattice shown by the different colored arrows here. And from these local arrangements, you can generate any local environment simply by shifting and rotating finite structures. This is very helpful, and we were at that time working very closely with a group of mathematicians who developed a very formal way to express this. Basically, you can go from integrals in the Brillouin zone in reciprocal space, which is typically what we do in physics to obtain observable quantities, to integrals over local configurations denoted by small omega over all the possible configurational space arrangements, which is covered by capital omega. So this description in terms of these local configurations can then give you a very accurate and mathematically exact description of the system. But in order to do this, you need a Hamiltonian with finite range. And indeed, we worked very hard to produce such a finite range, real space Hamiltonian. This can be produced by going from block states to tight binding Hamiltonians with localized Wannier orbitals as their basis. This is a standard type of approach referred to as producing maximally localized Wannier orbitals and making it transformation, a unitary transformation of the Hamiltonian from reciprocal space, from K space to real space. The surprise when we did that was that the orbitals, the Wannier orbitals that you need for an accurate description are not just the PZ orbitals that we typically assume that I showed you earlier, but they're more elaborate wave functions, single particle wave functions that look like this, and you can decompose them into the PZ orbitals with angular momentum 0 and higher angular momentum states shown here schematically. This was the work of my student Shang Fang. And then you can construct an interlayer interaction, this hopping matrix element between layers that includes all these terms, the V0 term, which comes from these interactions, the V3 term that comes from the next angular momentum contribution, V6 term that comes from the next angular momentum, and so on. And these are not negligible. This term is about 25% of the strength of this, and this is about 5% of the strength of the first term. So they're not negligible. But this gives us then the ability to do very accurate calculations, and that's how we were able to produce this picture for very large systems, including of order 1 million atomic sites. So what you see here is the density of states on the vertical axis. It's also color coded. 0 is dark blue and high values is yellow. This is the angle axis going from 0 up to about 5 degrees, 6 degrees. And this is the energy. And again, this is the Fermi level, the position of the Fermi level in the charge neutrality system. So this is the 0 twist. So you have the single layer density of states with the small humps here, the small increases here, the Van Hove singularities that I mentioned earlier, which are far from the Fermi level. But as you increase the angle, you can get very high density of states right at the Fermi level. And these are the flat bands, the effect of the flat band. So we named this effect to Stronix, and then it caught up. Magazines like Physics World picked it up, and now it's quite popular, and it even has its own Wikipedia entry. So here's the bottom line.
There is a question.
Yes, please.
So are these Wannier functions still centered on the atomic sites? Or
Yes.
they appear in empty Wyckoff positions?
No, these are atomic site-centered Wannier orbitals. So that's what this green arrow indicates. There's an interaction between atomic sites, each atomic site having this full Wannier function.
Thanks.
Okay. So this is a picture now. So this is the localized electron states in real space. And I hope this will answer one of the questions that came up at the end of the previous talk. So this down here is the bilayer graphene. So these indicate the regions of A-B stacking here, BA stacking here, and AA stacking here. And the vertical axis here is the local density of states, of electronic states in real space. So this is where the electrons actually really reside in real space. And as you see, they are strongly localized at the AA sites, right around here. And this has important consequences, and I will come back to it. And these are the flat bands at 1.08 degrees. Just for comparison, this is now a three-dimensional view of the bands. Kx and Ky are the plane here on which the reciprocal space vector exists, and the vertical axis is the energy, and these are the flat bands. So these are the density of states here that come from the flat bands. So you see this is the density of states at 1.05 degrees. And for comparison, this purple line is the single layer graphene density of states multiplied by a factor of 1,000. So you see how small the density of states coming from graphene itself is, and how big an effect of the flat bands are. However, the bands are not completely flat. And in fact, you can never get completely flat bands. The bands always have some dispersion. And if one band becomes very flat, the other has considerable dispersion. And at some point, their dispersion flips and so on. So I wanted to emphasize this. The bands are never completely flat, at least in this single particle picture. So one important question is what happens to the atoms? I showed you the overall distribution of atomic sites when you put one layer on top of each other, but the atoms don't stay where the original layers were. They relax to minimize the energy. And the first study, the first detailed study of the effect of relaxation on the rotated, on the twisted bilayer graphene was done by this group, Zhang and Tadmore. And here's the picture that they produced using an interatomic potential to model the interaction between atoms and that allows us to calculate the relaxation, the atomic relaxation. So this is before relaxation. You see this AAA stacking, as I mentioned earlier, I described earlier, BA and AB stacking, and the boundaries between them, these are called also domain walls. And this is what happens after relaxation. The AB and BA regions expand significantly because those are the low energy structures. The AA regions contract very significantly. They shrink to very small regions. And there's an additional twist of the AA regions beyond the twist imposed on the entire bilayer system. So the local rotation is the original twist of the entire, the relative twist of the two layers, plus an additional twist at the AA regions. So here's a slightly more detailed view of this, of what happens in two key features of this relaxation. So this is the horizontal axis in both of these plots is the initial rotation, how much rotation you impose on the two different graphene layers. And in the first plot is a picture of the local twist, the additional local twist that I mentioned. So if you go to large angles, about 2-3 degrees or so, the theta 0 basically is proportional to the initial rotation. And if you go to smaller twist angles, the local twist flattens and becomes constant. And this is the width of the these are called saddle point configurations or domain walls. So these domain walls become smaller and smaller in width as the angle increases, and they acquire a roughly constant size at small angles. And the behavior changes at around 1 degree near the critical or so-called magic angle. So below the magic angle, you have constant diameter of these AA regions and constant twist angle.
Tim,
Yes.
there is another question.
Yes, please.
But if the flat bands are topological, they shouldn't be Vanier representable since they don't have an atomic limit. It is surprising that a Vanier model can reproduce the flat bands, or is the topological character not reproduced correctly?
I'm sorry, I'm talking about a single particle picture here. No, the mean field theory, a standard single particle picture. So that produces a band structure. In order to have a band structure, you need a set of atomic positions. You can't have a band structure of something that doesn't have a lattice in real space. That's what I'm talking about. So the flat bands is a consequence of the band structure, the Moiré supercell of the atomic positions that are produced by this relaxation. And I'll come back and discuss that in some more detail. So this is a single particle picture. Okay, so the flat bands are produced by the atomic configuration, and it's the sub-bands, the splitting of the bands, that is a consequence of correlated behavior. Okay. Okay, so what I just described to you was based on interatomic effective potentials. This is an approximate description of the energetics between the interaction of the layers. So, but we can do a fully ab initio interaction of the different layers, and this is based now on density functional theory, the standard ab initio approach. And the way that we do this is by calculating what is known as the generalized stacking fault energy. So as a function of configuration, so this is what the energy looks like. For graphene, this is the black line. So imagine sliding the two layers of graphene on top of each other. And this is the energy landscape that you can generate by this. And if you take a diagonal cut through this energy landscape, this is the line, the black line. The other two pictures correspond to molybdenum disulfide at 0 degrees and molybdenum disulfide at 180 degrees, the red and blue lines. Let's not worry about this for the moment. This is just to indicate that we have looked at many other systems, not just graphene, and especially to the transition metal dichalcogenide systems. So now you can take this energy landscape. So this is just energy as a function of sliding, and use a very nice theory that was introduced about 30 years ago by Jim Rice, and is based on the theory of dislocations, and use this to produce the atomic configuration. So this is essentially the gradient of this energy landscape. You take this energy landscape, you calculate its gradients, and the gradients can give you the atomic relaxation. So this is what I'm showing you here. So this is now, the arrows represent the amount of atomic relaxation in different regions of the supercell. And this is a schematic of the relaxation. So black is basically no relaxation. So at the center of these triangles, which are the AB and BA regions, there's no relaxation. But at the boundaries, there's a lot of relaxation, and especially at the corners, which are the AA regions. So using this, you can produce now this pattern, and this includes full relaxation of the atoms. So you see these AA regions, these domain walls, and these AB or BA regions, the low energy regions, including the full relaxation of all the atoms in the graphene bilayer. This is the corresponding picture for molybdenum disulfide, but as I said, I don't have time to describe both types of systems. We'll concentrate on graphene. And again, this is the graphene picture. Molybdenum disulfide, the other two panels. Let's concentrate on the panel on the left. So what I'm showing you here is the results of this relaxation in configuration space, and how that translates to positions in the real space. And as you see different panels here. As you go down the column, you start at 2 degrees twist, 1 degree, and then smaller twist angles. But you see that the pattern in real space at large angles is very confused, so to speak. There's no clear regions here. At 1 degree, the regions start to appear, and if you go to smaller twist angles, the pattern does not change, only the black regions increase, and everything else stays the same. So you just expand the scale of the system, but nothing else changes. So this is indicative that at around 1 degree, these regions have fully appeared, and they don't really change character anymore. They just change size. The black regions and everything else more or less stays the same. So, so this is essentially the picture that comes out from the atomic relaxation. So you see two graphene layers here. This is the top layer, this is the bottom layer. And the color coding here, the color scheme tries to capture the relaxation. The A, B, and BA regions are closer to each other. There's a relaxation on the vertical axis as well as in-plane relaxation. So these are the two regions closest to each other, and the AA regions repel each other, and the distance of the atoms in the AA regions is farther apart than the normal graphene interlayer spacing. In the distance between layers in AB regions is 3.35, in AA regions is 3.60. So that's about a 10% increase, which is quite significant.
Tim, you have 2 more questions.
Okay, thank you for pointing this out.
Are symmetries broken by the relaxation? That's one.
Yes, yes, symmetries are broken by the relaxation. Yes, there's the overall pattern symmetry, but local symmetries are broken. Are these pictures of Vanier real configuration? Are these pictures of Vanier real configuration are for one valley, or do you consider both valleys? Okay. So this is atomic structure where the atoms are. There's no Vanier orbitals here and no bands yet. So there's no valleys at this point. This is just positions of atoms representing the positions of atoms in the real space. So next comes the bands that are associated with this. So here are the bands now. So first on the right, I am showing you the bands without relaxation. If you don't allow the atoms to relax at all, and you just put one layer on top of each other, and you see clearly this is wrong. This has nothing to do with experimental observations, as I mentioned earlier, with mini gaps and with the gaps and flat bands and so on. So this is the band structure, electronic states. So the vertical axis is energy of the electrons. The horizontal axis is momentum in reciprocal space. So these are the high symmetry points in the reciprocal space, K, gamma, M, and K. So these are the bands now. And you see the flat bands, but only after you have taken into account the full relaxation of the atomic sites. And I'm showing you two sets of bands here. So the black bands are produced with the tight binding Hamiltonian that I described earlier, using as a basis the localized Vanier orbitals. So the Vanier orbitals associated with every atomic site in real space produce these bands in reciprocal space. And this is now the picture that everybody refers to, the flat bands. But as you see again, the flats are never completely, the bands are never completely flat. There's always some dispersion. And there are gaps separating them from other energies. So the red lines are an effective simplified Hamiltonian, a K dot P theory, where you expand the bands locally near the high symmetry points, and that's the simplified Hamiltonian produced to approximate the full tight binding Hamiltonian. Okay, so here's the real space again. Positions of atoms, blue and red layers in real space. And here are the bands in the reciprocal space. And again, the bands without relaxation are black. The bands with relaxation are red. And you see the gaps that appear here only when you include the relaxation. And without relaxation, there's essentially no gaps. However, interestingly enough, the shape of the bands does not change very much with relaxation. It's just that the bands shift and produce these band gaps.
There is another question.
Yes, bands are clearly different with and without relaxation, but how do the genesis of bands change? Is this change consistent with the symmetry breaking relaxation? Yes. The symmetries are mostly preserved, and I will say a little bit more about this in a moment. So, let me elaborate on this actually in the next few slides. So before I do that, let me point out something very important. Here is again the picture unrelaxed in, for the bands. This is just the flat bands at 1.11 degrees. And so on. So this is the picture with the full relaxation. And this picture now contains several important features in how they depend on the twist angle, as including the full relaxation. So this is the picture that I want to describe in some detail. So the blue lines here are the width of the bands, shown here schematically as the band width, the flat bands. Okay. The red lines are the gap between the flat bands and the other bands. So these are the red lines shown here. And you see the results for the electron up here and the hole. So there's definitely a broken electron hole symmetry. According to this set of calculations in this picture, there's no electron hole symmetry here. It's broken. And the dashed line here, the black dashed line, is the Fermi velocity. So this is the twist angle. And you see that as you change the angle and you make it in a small region around 1 degree, then all these features become optimal. So the bandwidth, the blue, becomes the smallest possible value. The band gap, the separation from the other states, becomes the largest possible value, the red lines. And the Fermi velocity, the dashed black lines, becomes also smallest. So the Fermi velocity is, of course, the flatness of the band. So you have very small Fermi velocity. But there's a region where these features are optimized. So it's not just a single angle. So sorry about this. It's not just a single angle, it's a range of angles. So it's not just one magic angle value, it's a small range of magic angles. Okay, so here's also a comparison with the Bistreitzer and McDonald model. So this is the green line. This is a quantity called alpha square, which is basically proportional to 1 over the twist angle. So as alpha becomes larger, the twist angle becomes smaller. Okay, and this is the region around 1 degree. So the Bistreitzer-McDonald model predicted a 0 value for this quantity, which is the magic angle at this point, and it also predicted other 0 values. So there was the suggestion that there may be several magic angles. If you have a model without relaxation, these minima are roughly at the same places. If you include full relaxation, this minimum persists at exactly the right range of values, but there's no other minimum. Okay, so this model, including full relaxation, suggests that there's only one small range of magic angles. Okay, so how do you construct now a many-body theory using as input this information? And I think here some of the questions that were raised will be addressed more clearly. So what we do is the following. We start with a chiral symmetric model. So this is the simple model introduced by Bistreitzer and McDonald, and also elaborated on by several other people, and was mentioned by Celine in the previous talk as well. So in this model, you can clearly identify the symmetries of each band. So this is M symmetry, C3 symmetry, and so on. And you can clearly see what kind of band structure with full symmetries this model produces. Then we use as guess states that come from this model and use these to project the ab initio bands. So these are the bands that I just described to you that come from the ab initio Hamiltonian model, and we try to fit by producing a model with a few bands that captures the ab initio band structure with full atomic relaxation. So we start with these states that are inspired and include the symmetries of this model, and they are centered at this following position. So there are two states with different symmetry, S and P-like symmetry at the AA regions. These points are the AA regions. Then there's a third state with S-like symmetry, which has also its center at the AA region. And then the next states, labeled 4 and 5, are centered in the AB and BA regions, at the centers of these two large triangles, where the low energy atomic configurations exist. And then we have 3 more states, 6, 7, and 8, which are centered at the domain wall boundaries. And we need all of these 8 states to capture the band structure. So we start with the chiral symmetry states as guesses, and we use the proper combination to reproduce with a few adjustable parameters the full band structure of the system. Okay, so these 8 states produce this band structure in the chiral symmetry, and then we adjust the parameters to make sure that of the Hamiltonian of these 8 states, to make sure that they fit very accurately the band structure of the ab initio calculations. Because if just these states do not reproduce the band structure of the ab initio calculations without adjusting their parameters. So having done this, we produce the following picture. So the full band structure is shown here. The band structure fitted with 8 bands is shown here, which is very, very accurate for a reasonable range around the Fermi level. Just keeping 5 bands, the 2 flat bands and 3 bands above, 5-band model is this. Just keeping 5 bands with 2 flat bands and 3 below is this. But going to just 2 bands cannot reproduce this picture. That's the message that I want to get across. So here is now the best model that we can produce, consisting of 8 bands. The bands labeled 1, 2, and 3 are centered at the AA regions. This answers the question that was raised in the previous talk: where are these electronic wave functions? Here they are. Bands 1, 2, and 3 are centered at the AA regions. Bands 4 and 5 are centered in the AB or BA regions. And the bands 6, 7, and 8 are centered at the domain walls. So these 8 bands together produce a very reasonable representation of the ab initio bands. And you see that you need all of them because they are very strongly coupled. So let's look at one state. Let's look at this state, for example. So this state projected on the bands has large projection on those 2 bands, and it has large projection on this part of the flat bands and large projection here. The other band here has large projection on those 2 bands and smaller projections here. The other 2 bands, 4 and 5, have large projections here and here, but also a very significant projection here. So all these 8 bands are strongly coupled, and a 2-band model just simply does not reproduce realistically the physical picture that arises from the single particle calculation. So we have done lots of calculations of similar type for other systems. So this is molybdenum disulfide with molybdenum molybdenum disulfide with a small twist angle, also from the Philip Kim group. Different patterns here for different orientations. Near the 0-degree orientation, near the 180-degree orientations. Those are the 2 low energy configurations for this material. And you see similar patterns, and we have done similar calculations with configuration space analysis of the atomic structure, with analysis of the density of states in configuration space and in real space, very similar type of behavior, but in very different regions of the energy of where these states lie. I don't have time to describe this in more detail. I'll jump very quickly to another system, which has to do more on the work that we are currently involved in. We are now focusing quite a bit on the twisted tri-layer graphene system, because as I mentioned very briefly at the beginning, this is a very exciting system, much more complicated, but also much richer. And we think it holds promise for exploring lots of interesting physics. Just to make a comparison, here's the twisted bilayer graphene system again. I showed you this picture earlier. I believe you should be familiar with this. The 2 Dirac cones, red and blue, intersecting here and producing the flat bands. There's 1 twist angle, and the cell size, the real space configuration cell size, the Moiré pattern, is proportional to 1 over the twist angle theta. So here's the twisted tri-layer graphene. So not surprisingly, there are 3 Dirac cones here. So the blue Dirac cone, the orange Dirac cone, and the black Dirac cone, the 3rd one. And of course, you see again flat bands, which come from the splitting of the bands where they intersect. But also there's additional bands here. There's more bands here, and there's also a Dirac cone in the middle of the flat bands and so on. Moreover, this is a much more challenging system because there are two different independent angles for the twist of the layers, the top and bottom layer relative to the middle layer, and the cell size increases as 1/θ squared because of the two different patterns. And this makes the calculations very, very difficult and quite challenging. Interestingly enough, the phase diagram, again, this is the temperature on the vertical axis, the doping on the horizontal axis. So this is the phase diagram of the different phases. Again, reveals superconductivity. So the blue regions, again, correspond to superconducting states. Here's the picture experimentally that shows the superconductivity when the voltage versus current picture. The VI curve shows a flat region. And interestingly enough, the critical temperature for superconductivity here is 3.4 degrees Kelvin. This is about a factor of 3 or 4 larger than the bilayer system. So this is very promising that the superconductivity is at significantly higher temperature. Therefore, the correlations more interesting, stronger, and more promising for actual applications. So this is a project in which my student Zoe Zhu is concentrating her efforts, and you'll hear from Zoe also a little bit tomorrow. And this is a short overview of the kind of atomic relaxation that you see in this system. And this is what we call a moire of moire. So we don't have just one moire pattern, we have a moire of another moire pattern, and this gives very complicated atomic arrangements, layer 1, layer 2, and layer 3 with blow-ups of the atomic configurations. Again, this is showing the positions of atoms in real space as calculated by the type of calculation that I showed you earlier, and Zoe will elaborate on this tomorrow. This gives also, let me just show you very, very quickly, much more complicated band structures. So this is the bilayer band structure. So these are tri-layer band structures along different directions in K-space, and it's a mess, but we can make sense of this mess, and Zoe will be describing some of the details of how we make sense of this big mess of states associated with the triangle. So I'm going to stop here because my time is over. I'm just going to give credit to the 3 students, Shang Fang and Stephen Carr and Zoe Zhu, who were at the forefront of this research. But it's a collaborative effort. Many more people were involved in these types of calculations, and the models and the results that my group has produced. I wanted to briefly mention them. So Daniel Larson, Cedric Flaman, George Sinsaris, Sharmila Shirodkar, Grigory Kolesov, Iana Pompeo, and Marius Matakis. They all contributed very importantly here to the work led by these 3 students. We have collaborated very closely with many experimental groups, in particular with Philip Kim and Pablo Hariri Ferrero, and we have had great help in the math modeling with the group of mathematicians that I mentioned earlier, led by Mitch Loskin and several other people with whose groups we have interacted very strongly to discuss the issues of how you translate this single particle picture to a more elaborate many body picture. So I'll stop here and take questions. So let me see, there's a question in the Q&A chat already. So let me try to read it. There's a question about the Wannier function construction on the bands near Fermi of twisted bilayer graphene. Does the impossibility to construct Wannier functions of only the 2 middle bands come from some topology? And how can you make sure that for the other model, 5 and 8 bands have exponentially localized Wannier functions, or maybe you don't need it? Well, what happens in this construction of the Hamiltonian that I showed you? Okay, So this is the set of steps that we take. So these are states that were generated from so these are states generated by the chiral symmetric model. Okay, so these are states localized in different regions, and they come from a very simple model. So we use these as the basis. So that's the band structure surgery. We use this as the basis to project the bands from the ab initio calculations and create a Hamiltonian that reproduces these bands. So there's no more Vanier functions involved here. Okay, there's just these localized states, and the Hamiltonian based on these states is adjusted. There are several parameters involved in this Hamiltonian, and those parameters are adjusted to go from this picture, which doesn't fit the ab initio bands, to this picture. Has this answered your question?
There is another one.
Yes.
Okay.
I don't see the other. Oh, yeah. Okay. Yes. So the bands you showed are K dot P theory expanded around the gamma point. Okay. How large are the unit cells? Okay. The unit cell here is basically generic. It doesn't correspond to a particular unit cell because you do the expansion near the gamma point or near another high symmetry point without reference to the the actual unit cell. These bands, the ab initio bands, come from specific unit cells, and these unit cells are very large, of the order of 100,000 atoms, close to the region of the magic angle. And as I said, there's not a unique magic angle value. There's a small range of magic angle values, so we play with that range to produce a reasonable band structure. Okay, did that answer your question? Okay.
Are there more questions before we close the session?
So
Otherwise, we'll have a Slack. Oh, okay.
may
sorry.
I ask a question?
Sure.
Please do.
So Tim, you mentioned these mores of mores, and I guess you're looking, you and your group members have looked at the relaxation that occurs in those cases. Are there any sort of design principles for what relationship between one more and another would give rise to some to some meaningful structuring of the bands?
Yes, yes. So yeah. So this the example that I showed you has the first twist angle at 1 degree and the second twist angle at 0.33 degrees. So this is just to give you an impression or a sense that we can do calculations for a wide range of possible twist angles. We don't have to restrict ourselves to any particular case. Some groups do very nice theory, but certainly limited to a sandwich with the top and bottom layers aligned and the middle layer different orientation. So anyway, so we can do a very wide range. We have explored this very wide range to come up with design principles, as you are suggesting, but this is going to come out as the result of the calculations that Zoe will present tomorrow, and I don't want to steal the thunder from her presentation.
Thanks very much.
Okay, so you'll see all this tomorrow. There's lots of very nice, interesting results.
Okay. Are there more questions? If not, let's thank Tim again. And we reconvene at 5 p.m. with David Gold-Haber-Gordon. Enjoy the break.
Thank you.
Okay. So you're a panelist now. Maybe you want to try to share your screen. Or...
Yeah, thanks. This should be working. Can you see my screen?
Yep. Yeah, it seems to work fine. We can hear you. We can see your screen. So.
Okay, great. Thank you so much.
Okay, thank you very much. I really appreciate that. So Zoe and I will join tomorrow, and at some point we'll transition, and then she can describe her work. Thank you very much.
Anyway, there is a Slack channel where you might get more questions and you can interact with the students.
Fantastic. I'll check that right away. Okay.
Either you or Zoe can interact with them. I mean, as you like.
Okay, Zoe, you have the information?
I don't.
Okay, I'll forward you the information.
Okay.
Yeah, you can send. We can send you. If you send us your email, we can send you a Slack invitation, and then you have access to all the channels. But the organizers one.
Yeah, I'll drop my email in the chat now.
Okay. All right.
Okay, thank you very much.
Okay.
I need to go.
All right.
Thanks for the invitation.
Thanks
Thank
to
you
you.
very much. Yeah.
Bye
I'll see you
bye.
tomorrow.
Okay, bye. Hi, Dave. Hi, how are you?
I'm fine. I'm just, I wasn't sure how to find the previous talks, and so I'm just trying to make sure that I'm. So I saw the schedule and a couple of the notes on the webpage about what people plan to talk about, and so I think I can. I think that what I'll be saying is reasonably aligned, but I guess Rebecca was talking about some experiments, and I'm trying to remember the just a second, the I think Cecile was talking about theory of orbitally ordered multi-layer moire graphene. So I since I'll be talking about experiments in that area, I just wanted to know whether there's any guidance about what was covered or what was particularly interesting to people. But
well, I think probably nothing really close to your experiments was already
okay.
Because Rebecca was talking mostly about valley hole, related currents and so on, and I think the closest talk to my knowledge has been probably Cecile, but it has been mostly from a theory point of view. So
okay, great. So
I think whatever you prepare is going to be great. But if you really want to know, maybe for tomorrow, what has been said, we have actually a YouTube channel where we have been uploading the videos, so you can scroll through. I'll send you the link by email, maybe.
Great, that sounds good. Thank you very much. Sorry for. Good to see you, and I'll be on in a moment.
Sure, no problem.
if you want to try your screen, or by the way, we cannot see your camera. I don't know.
Yeah, no, I'll turn that on. Yeah, I'm just
Oh yes,
it's early morning here, so I'm just
yes. Yeah, I understand.
thanks. So may I try screen sharing?
Yes, go ahead. Go ahead. Hello.
So I always forget how to do you see the correct full screen one, or is it?
Yeah, it is good.
Okay, great.
You want to try just the passing slides, something just to check that I'm seeing. Yeah, that looks good.
Okay. Great. So I think that my helper will probably go away in a minute, but
well, we probably will wait a couple of minutes after 5 to start. We will not start sharp on.
please wait half an hour.
What can I do? Turn on my iPad.
Hello, everybody. So it's almost 5 p.m. Central European time, and it's the time for the next lecture from David Gordon from Stanford University. And he's gonna talk about what kind of magnet can carbon make. So welcome to the school, David.
Thank you very much, Maya, and thanks everyone for.
You can't be in San Sebastian, but hopefully in the future you can come visit us. And the screen is yours, so whenever you want, you can start.
Great. So if people, so first of all, let me say that during the talk, if you have a question and it affects how you're able to follow the flow, please don't hesitate to ask. Probably someone else has a similar question, and I'm happy to have you jump in. And if you try doing it in the chat, I'm not certain that I'll see it, so don't hesitate to just call out and ask. But anyway, it's really exciting to participate in this summer school. And I thought that since Cecile has probably told you a bit about some of the theory of orbital states in graphene-based stacked systems, that I'll tell you a story of adventure and discovery. And today I'm going to tell you about discovering orbital magnetism. So in a sense, I'm stealing the thunder of the title, but I know you've already heard a bit about this. And tomorrow I'm going to tell you about a second attempt to reproduce this and the new adventure that set us off on. So, so just let me start by setting context. I know that you've heard from Pablo Herrero and from others probably about the theory of strong correlations in 2D electron systems based on mores that you just heard from Tim Kaxiris about some sophisticated calculations of the band structure that leads to this. But I think for much of the field, the awareness of the possibilities here came not with some of the first theory a decade ago, but with experiments from Pablo Herrero's group, where they saw that for twisted bilayer graphene, you could get states that did not look anything like what you'd expect from simple band structure. There were correlated insulating states, and especially superconductors, and this created a lot of excitement in the field. And this was relatively soon reproduced by Columbia with Matt Yankowitz, the lead author there, and eventually by quite a lot of other groups. And as you heard from Tim Kaxiris, the basis for this is that you end up with some set of bands that have nearly flat character, very little variation of energy with momentum. And so that upends the standard paradigm that we have in theory of metals. Normally, you fill the lowest energy states and then higher and higher until you run out of electrons. And the Fermi level is a boundary between the filled states and the empty states. But in this case, if all the states that you're trying to fill have the same energy, then you have a lot of freedom in which ones you fill, and you can fill them based on what will minimize the Coulomb interactions among the electrons. And of course, that's an oversimplification. Not all the states that we're trying to fill don't all have exactly the same energy as you saw in Tim's group's calculations, but still the Coulomb interactions can be strong compared to the dispersion of the band, and in that case, they play a big role and can give you almost anything in terms of states that emerge. So, so these, just to remind you, these samples are made by picking up a stack of atomically thin layers. I'm happy to answer questions about specifically how we do it. This field has been really characterized by different groups helping each other, being very generous about sharing their approaches and techniques, and I definitely want to pass that on also. But ultimately, we end up with some very atomically thin layer. In the case that I'll talk about most, 2 layers of graphene with a twist relative to each other that are protected by a dielectric above and below, and then miraculously can be contacted from the side. This is coming from work from Columbia, showing that you can make extremely robust contacts to just 1 nanometer or so that's poking out of the graphene at the side, so you can leave most of it protected. And so here's an example of a completed micrograph of a completed sample that we've made, and you can see that there's metal on top. That's a gate electrode. There's also a gate below, and so what that ends up allowing us to do is to, by tuning these 2 gate voltages, you can see that there are features in conductance that we measure through this structure. So in this case, we're plotting a resistance, and you can see there are features that have some systematic behavior in these 2 gate voltages. And what you can notice is that if you vary the 2 gate voltages in opposite directions, then you're going to stay at the same carrier density in the sheet, but you'll change the electric field, what we call a displacement field, normal to the plane. And on the other hand, if we change the 2 gate voltages in the same direction, we'll change the density. And this is a sample that was at a little bit above the magic angle, 1.20 degrees, as compared to 1.05 to 1.1. That may seem not very much, but it turns out even hundredths of a degree variation can make a difference in these samples. So let's look a bit more at these measurements and see what we can get out of them. So I'm now going to depart from the historical structure and to tell you that we had unintentionally aligned the lattice of this twisted bilayer graphene with the lattice of the cladding layers. I just referred to them as a dielectric, but I think you've heard during this summer school that the most typically used dielectric is hexagonal boron nitride. It has almost the same structure as graphene, but a slightly different lattice constant. And it turned out we had accidentally aligned the boron nitride in one of the two cladding layers almost perfectly to the two twisted graphene layers. And so this was our early attempt to reproduce Pablo Herrero's group's work and to see superconductivity. And as you'll see, we didn't see that. And that turns out to be a consequence of the alignment with the boron nitride. So later on, we made many more such samples, and this is a case where we intentionally did not align the boron nitride. And so I'm just going to compare the data from the two. So in the case where the two are not aligned, I've now mapped the data into a space that makes more physical sense than gate voltage. This is the displacement field in the on the vertical axis, the field normal to the plane, and the density on the horizontal axis. And I've also changed to natural units for density, which is 1 means we've completely filled the moire band. -1 means we've completely emptied the moire band. This nearly eightfold degenerate band is half filled when we do not apply gate voltage, and this is called the charge neutrality point. And on the top, I've listed units of density per centimeter squared of electrons. And what you can see here is that there are a lot of features that are all vertical and that don't change very much with the vertical axis. That's telling you that the electric field normal to the plane doesn't matter very much in this case, but the density does. And so, for example, this feature at 0.5 means when in a situation that you would normally expect to be just a partially filled band, a metal, instead there's a pretty high resistance. So this is something that's familiar from magic angle graphene, that you can get correlated states insulators that occur at partially filled bands. So now let's look at the one with aligned boron nitride. And at first glance, it looks quite similar. Again, we have basically vertical features, but you can see that actually those features do change with the electric field normal to the plane and in an asymmetric way, which suggests that the structure is asymmetric. Indeed, that's because of alignment with one of the boron nitrides. It's not the same on top and bottom. And then if you look more closely, you'll see that the scale of resistance that I showed is actually much higher in this case. And so I find that color maps like this can make things really jump out that you wouldn't notice otherwise, but I also like to say that they can hide a multitude of sins. And so it's really useful to look at line cuts through them to get more quantitative sense of what's going on. So let's take cuts in these two cases at fixed displacement field, but varying density, and see how they look. So I apologize for the coarseness of these data. I haven't replaced them with more recent ones, but what you can see here is that at the charge neutrality point, there's a peak in resistivity. And there's a peak when you have the band completely filled or completely emptied. And then there are peaks also at half filling the upper part of the band. But if you look at these resistance levels, as I mentioned, they're relatively modest. In this case, say 2 kiloohms. So 2 kiloohms is a fine resistance value for a graphene sheet. It turns out that graphene, unless you can, graphene is resistant to localization because of its topological structure, or let's say because of the structure of its honeycomb lattice, and if you don't do something to break the symmetry of the system, the resistivity of a single sheet of graphene cannot be larger than of order the quantum of resistance, or more specifically about 20 kiloohms in this case. And so a couple of kiloohms is a very typical resistance for a graphene sheet or two. In contrast, in the aligned HBN case, the resistivity is 100 kiloohms, and that's higher than 20 kiloohms. It's too high to get in graphene without breaking some symmetry. And so that tells you something strange is happening. In addition, there are features that are not at simple multiples or simple fractions of fulfilling. So fulfilling represents 4 electrons per Moiré cell, and here -4 electrons per Moiré cell. And you can see that there are extra features outside here. Those turn out to be related to the density at which a graphene boron nitride Moiré is filled. So there are some indications that something's a little bit strange here. And in fact, when we looked back at our photos taken during construction of the sample, you can see that the graphene and the boron nitride have facets that are almost aligned. So one could see by looking at this that it's aligned to within about 1 degree, unless it's actually off by 30 degrees, and we can't tell which facets they are, but it turns out it's aligned to within 1 degree. All right, so it was already known for a while that alignment with boron nitride can change the behavior of graphene, even though I said that boron nitride is typically thought of as a pretty inert dielectric. Both my group and Pablo Herrero Herrera's group had found 8 years ago that that graphene can have monolayer graphene that should be always a conductor, can have very high resistance at the charge neutrality point, and Pablo's group in particular showed that that alignment with the boron nitride can modulate how high that resistance gets. And the idea is that as I mentioned, you need to break asymmetry to get a resistive state there, or an insulating state there. And you can do that if you align with boron nitride, because then, let's say, one carbon atom is sitting above or below a boron and one sitting above or below a nitrogen, and you break the sublattice symmetry locally. So just to give you a somewhat concrete picture of what's going on here in this complex stack, here's a cartoon of just one layer of graphene, hexagonal lattice. Now let's put another layer on top, and here we get Moiré, which I think you've been seeing a fair amount during this summer school. And now we're adding on something sort of like what Tim Kaxiris mentioned near the end from Zoe's work. We add yet another layer, which in this case is the boron nitride. And since we know the twist angle from our electrical measurements, we can actually say how it's aligned. And adding the boron nitride, interestingly, produces a Moiré that both has almost the same period. So if we zoomed out, we would see that these two Moirés were beating against each other. But actually, this Moiré not only has about the same period, but also is at the same rotation angle, which is not trivially something you'd necessarily expect. So, so when we realized this, I said, the strange things that I'm going to show you, there are three possibilities. One is that all that's necessary is that the boron nitride is roughly aligned with one of the graphenes, and that it breaks the symmetry. Another possibility is that it matters what the specific orientation of the graphene boron nitride moire is, and the specific period of it is, and that we were just extremely lucky. And third possibility is it matters what it is, but the system likes to relax into an orientation that the two moires are matched to each other. And my feeling was that the second one was very unlikely, that we were just too many coincidences happening. But the truth is, we actually still don't know what the answer is. Alan McDonald's group has done calculations suggesting that actually the orientation of the graphene boron nitride moire matters. So, all right, so we were just starting to characterize this sample, and my student, Aaron Sharp, was doing Hall measurements just at very low field, a low magnetic field up to 1/10 of a Tesla, 1.5 Kelvin. And you can see that there's a small Hall slope. This is at 1/8 filling of the upper band. That's half an electron added per moire cell. This is at 2 electrons per moire cell, 2.5 electrons per moire cell. You get these small and varying Hall slopes, which allow us to sort of diagnose how we're filling the band. And then at 3 electrons per moire, something changed. And this was really quite striking. Now the Hall slope is quite steep. It's going up in tens of millitesla. It's going up to a couple of kiloohms, a very substantial resistance, and it's not linear. It's now plateauing. And so this was quite striking. So Aaron was disappointed that he wasn't seeing superconductivity in this sample, but he thought this was interesting enough that it was worth cooling the sample down to lower temperature. And so now I'll show you a measurement in our dilution refrigerator of the same thing. And you can see that now sweeping magnetic field over now a slightly broader range, you get a sharp step as you go through zero magnetic field. And quite strikingly, when we go back in the other direction, there's hysteresis. And the fact that there's hysteresis in magnetic field tells you that this is a magnetically ordered state. And so that's really quite striking. If you look more closely, you can also see there are multiple jumps here that suggest that if this is a magnet, it has multiple domains. Now, I mentioned that this was cooling things down. Oh, and also the size of the Hall signal has gotten bigger. This is, it's not symmetric about 0, but if you were to symmetrize it, it's about plus minus 10 kiloohms in size. So it's getting up toward, though not reaching, the quantum of resistance, which is what you'd expect in a quantum Hall system at high magnetic field. So this is really pretty striking and unusual. I mentioned that this was cooled down in a dilution refrigerator, but actually this measurement is made at 2 Kelvin. It turned out that this fancier cryostat was needed because we had better electrical filtering on it, because even tiny electromagnetic signals can shake up this magnet, as you'll see. So this magnetic signal is very tightly present at 3/4 filling, meaning 3 electrons per moire cell, or 1 hole per moire cell. So there's, I guess, 1 moment per moire cell, and these moments are aligning. There is a magnetic signal even out to much higher filling, but it becomes quite small. And also at 3/4 filling, we go from signatures of having electron-like carriers to hole-like carriers. So it seems like there's a gap or a semi-metal at that point. If we go around in magnetic field in a loop multiple times, you can see that the structure is quite reproducible, and these steps are not just noise. They're likely, as I said, flipping of domains that occur consistently at particular magnetic fields. The magnetism is stable if we don't apply a field. So if we do a hysteresis loop, come back to 0, and then wait for 6 hours, the Hall resistance doesn't change, and then we can keep on sweeping, and it's as if we never stopped. So this magnet is quite robust at these low temperatures. And in fact, the magnet lasts up to 4 Kelvin in terms of the, up to 5 Kelvin in terms of the anomalous Hall signal, and up to about 4 Kelvin in terms of having a hysteresis loop. So I plot here the size of the anomalous Hall signal, this step in the Hall signal, and it stays robust out to about 4 Kelvin, and then drops off rapidly. And the coercive field, the field it takes to flip the magnet, drops more steadily and becomes 0 at 4 Kelvin. So these don't require the millikelvin temperatures to see, but they are of course still low temperature. So what's going on with this magnet? The clues that we have are that there's a large anomalous Hall signal. Anomalous Hall signals have long been seen in ferromagnets, and normally they're milliohms or maybe ohms at largest. In this case, they're much larger than that, but they do diagnose magnetism. There's apparently an insulating state there. We see domains. This all looked a lot like earlier in the 2010s magnetic topological insulating films based on bismuth telluride. And so that suggested to us maybe what we were seeing was a Chern insulator, an equivalent of a quantum Hall system, but at 0 magnetic field. Now, ideally, that should have 25,812 ohms resistance, H/E². We saw a little less than half that, but that's not surprising if there's some disorder in the system. And so how could you get this kind of behavior? After all, we have a band that we're filling that can take 4 electrons per more, and we're filling it with 3 electrons per more. It should just be a metal. But if we allow the system to reorganize and polarize, then you could imagine one simple scenario is that it polarizes in both valley and spin. This fourfold degeneracy or near degeneracy gets broken, and we fill 3 of these valley and spin states and leave one of them empty, in which case we would be polarized, have a net polarization in both valley and spin, and we would have a net Chern number because of the valley. So, so that's a simple picture of what might be going on. And let me say that it was evident to theorists from the start, though it took me a while to be confident of this, that we were seeing valley polarization. And indeed, the first magnet that was built out of little circulating currents of the wave functions, instead of primarily out of spins, but theorists were very clear about that, because if you see an anomalous Hall signal, that can't come just from spin. If you have spin polarization, electrons are not going to deflect preferentially to the left or to the right unless there's spin orbit coupling. And carbon is extremely light, so you expect almost no spin orbit coupling. So having a very strong anomalous Hall signal strongly suggested that there is valley polarization, but not necessarily what's happening to the spins. So, so there were theory works that suggested how this could happen if you gap things out with alignment with boron nitride. or even that just electrons could spontaneously organize in gap. In the interest of time, I'm not going to go through this in detail, but I'd be happy to answer questions. There are typical kinds of measurements that people measuring quantum Hall like to make to diagnose whether there's non-local transport. There are 3-terminal measurements and 4-terminal measurements. And what you can see here in such a 3-terminal measurement is a signal, a large signal that's hysteretic if you're sitting right at 3/4 filling of the band, 3 electrons per moire. If you go even a little bit away, just a few percent away in filling, that signal goes away. And 4-terminal resistance is actually something that should have, ideally, this non-local configuration should have a 0 resistance. You drive a current on one side, measure a voltage far away from there. There should be almost 0 signal. And we see a signal, and it turns out that's because of a combination of non-local edge transport and also some diffusive transport in the system. So now we had surmised that this was likely a Chern insulator, but we didn't have quantization. And Andrea Young and his group searched their library of samples and found one that had alignment with boron nitride. And in one part of that sample, they were able to make measurements where they could actually see quantized resistance, showing that this indeed was a Chern insulator, quantum anomalous Hall systems, which is quite amazing that this just jumps out of this structure without any magnetic doping. So there are other striking things here. For example, we accidentally discovered by running too high, being too greedy, running too high a current in our lock-in measurements, that we lost our signal. And then we started trying to just drive a DC current through the sample. And we found that without any magnetic field, we could flip the magnet just by driving tens of nanoamps in one direction. And then we could flip it back with a current in the opposite direction. And Andrea Young's group verified this, that they could flip their magnet too back and forth. And there are a couple of different theories for how this can happen, but I would say it's not really fully explored and answered. And so let me now just say we've been trying to understand what this magnet is. I said it's almost certainly an orbital magnet, but to understand in more detail, we applied magnetic fields in different directions and specifically tilted relative to the sample. So this is a rotator where we can reorient the sample at low temperature and in 2 different axes so that we can change the out of plane field and also the in plane field, also the direction of the in plane field. And this is something we designed together with a company, AtoCube. And I mentioned a very simple scenario that we have polarization and we can fill 3 of the 4 polarized bands and not the 4th, but there's a proliferation of other suggestions for what could happen, some of them quite exotic, analogies to a composite Fermi liquid state suggested by Senthil and co-workers, something that I don't think has necessarily been suggested for this case, but you can get something that looks orbital that comes actually out of spins that are canted and that go around sweeping out a solid angle when you go around a plaquette. And so there are all kinds of things that could give this sort of behavior. And so we wanted to know what happens when we apply a field in the plane, which should couple primarily to spin, not to the valley. And so if we look at the resistance signal, the Hall resistance, as we tilt from fully out of the plane to 5 degrees from in plane, you can see it looks like a mess. But if we plot just as a function of the field out of the plane, then all of these collapse onto a single curve at low field. And what you can see is that really all that matters is the field out of the plane, all the way down to 5 degrees out of the plane, which is where the in-plane field is 10 times larger than the out-of-plane field. So that really tells you that this is a highly anisotropic system. The out of plane field matters, and that's what you would expect from little current loops. It's not what you'd expect from spins in graphene, which should be, all right. So I guess we're at the end of the time.
No, David, there is one question.
Okay, there's a question, great.
You still have like 30 minutes. Can you give
Yeah.
an intuitive picture in real space of this valley polarization?
So let me make an attempt at that, and there are possibly people on the call who may have better answers or something to add to that. So, so Mikkel, you heard from Tim Kaxiris that the bands that end up being closest to the Fermi level have electrons sitting on the AB and BA sites, or sorry, have wave functions that are centered at the AB or BA sites of the lattice. But what he didn't mention, but I think is correct, even in those first principles calculations, is that the primary weight of the wave functions is at the AA sites. And so what that tells you, if you have a wave function that's centered at AB, but the primary weight of the wave function is at AA, it means that there are 3 lobes of the wave function that are sitting at the neighboring AA sites. So it looks like a little propeller with 3 blades. And then in the 2 valleys, those blades are effectively circulating one way or the other. They have an angular momentum. So these bands are built out of wave functions that are little circulating currents, little propellers that are circulating one way or another. So I'm not sure whether that's an intuitive picture, but that's what I would say for real space. Does that help? All right, so I will.
He can talk, so I assume
yeah,
yes.
all right, I'm sorry. So, so yeah, so let me just say it's less understood what happens when we put on an even more in-plane field going all the way down to the plane. You can see these hysteresis loops get more complicated. And then we've gone all the way out to 14 Tesla, the maximum field that we can apply in my group. So this, here we polarized the system out of plane, then we rotated so that the field was in plane and started sweeping the field. And you can see that this big Hall signal disappears at around between 4 and 6 Tesla. And then beyond that, there's just some oscillation in the Hall signal, but it's just pretty flat. And then when we get below this 6 Tesla value, we again start to see a Hall signal that's hysteretic. And then when we go in the other direction, again, we come to a state where the Hall signal is not hysteretic. So it looks like there's some trend that at low field, relatively low field, we have at least 2 possible states, and we can flip perhaps somewhat randomly between them. But when we go to high field, there's some new state, and we don't yet know what it is, but I think that there's some effort to understand what's happening to the spin at those high fields. So this is not the only orbital magnet system that's now been discovered in graphene-based systems. So we collaborated with Feng Wang's group in studying ABC trilayer aligned with boron nitride, and they're in the valence band at 1/4 filling. So again, 1 hole per more. So maybe that has some important meaning. There's again a magnetic state depending on the direction of the out of plane fields. And more recently, there's been discovery by Matt Yankowicz's group and also I think Andrea Young's group that twisted monolayer bilayer graphene has magnetic states. So orbital magnetism and also Dmitry Efetov and others have seen that at finite magnetic fields, you can get orbital magnetism. So I think that this is going to be a rich area to play in. And in closing, I just want to mention something that I think is embarrassing and inconvenient, but important. And that is that there are, as far as I know, exactly 2 samples. This is a couple of years after we discovered this. There are exactly 2 samples in the world that show strong anomalous Hall effect in twisted bilayer graphene aligned with HBN. There are 2 samples in ABC trilayer aligned with HBN. I think there are now more than that in twisted monolayer bilayer, but it's not easy to hit whatever the conditions that are needed to achieve this. Very reproducible within those samples, many cool downs and many detailed studies, but I think this calls for more understanding of what really the design conditions are for this, and also for a re-examination of how we make samples. That that traditionally Scotch tape is used ever since Andrei Geim's work with Kostya Novoselov to peel off monolayers. You get random flakes, and then you pick them up in a stack with a stamp. And this is a picture of our stacking system. And there's a lot of control, but a lot of randomness in this. And that means that every sample is different. There are many knobs that we know are important, and probably ones that we don't know are important. There's sensitivity to even hundredths of a degree of twist, and strain we now believe is also important, including uniaxial strain. And so tomorrow I will tell a story of one of our attempts to reproduce this magnetism and what we found instead, which was again very interesting. But maybe I'll also speculate on how we can do better in control going forward. And so I just want to acknowledge the students who led this work in my group, Aaron Sharp and Eli Fox, plus many others who contributed. I mentioned magnetic topological insulators. The lens that I'm viewing these through was formed in part by working on those other systems that showed quantum anomalous Hall. I want to thank Feng Wang and Guorei Chen for collaboration on the ABC trilayer. And among the many people who've influenced my thinking, I especially want to acknowledge my late colleague Shoucheng Zhang, without whom I wouldn't have been thinking so much about topology and analogs of quantum Hall in these sorts of systems, well, in any system. So with that, let me say I'd be happy to answer questions. And I think that I have one in the Q&A from Lorenzo Rossi asking, does something similar happen at quarter filling? And if not, is there a rationale? So yeah, so Lorenzo, excellent question. You might expect that you'd see something at a quarter filling. You might expect it at a minus a quarter and minus 3/4 if the simple picture that I laid out of a completely flat band, and then you fill 3 of the 4 degenerate copies and not the 4th, all 4 of those places it should happen. Now, the system is not purely electron hole symmetric, either within the conduction band or within the conduction plus valence band that form this together, this 8-fold nearly degenerate band that has a bandwidth, let's say, of on the order of 10 millielectron volts at these twist angles. So it doesn't have to happen, but I would say there are calculations that suggest that it should happen at 3/4, but I think that it's not obvious, and I would expect that over time people that it will seen at other integer fractions, especially the ones where both spin and valley could be polarized. More recently, we have some work from ABC trilayer where we actually see an anomalous Hall signal, a magnetic state that is not centered at integer filling and we still don't understand why in detail, but I think that you will see such things happening at more fractions. And there's very recent work from Miria Kobe's group that shows almost down to zero magnetic field anomalous Hall states at a variety of fraction, so apparent churn insulators at a variety of fractions in twisted bilayer that they think is probably aligned with HBM. So Mikkel has another question. I mentioned extreme sensitivity to some parameters, such as the angle, and what's the accuracy we achieve in controlling these, and what's the success rate when creating these devices? So excellent questions. The precision with which we can set an angle is extremely high. So our motorized rotation stage, we can set to probably about 1/1000th of a degree. That doesn't mean that we'll get exactly that twist angle when in the end, and we evaluate the twist angle in part by the transport measurements by seeing what density we need to go to completely fill the band. And I can describe that in more detail if you're interested. But on the first sample I described, we were shooting for 1.17 degrees and we got 1.20 degrees. So pretty close, but not exact. That made me think, all right, we can probably hit the angle that we want pretty well. Later, we found that frequently the system that we're trying to put at a little more than 1 degree actually rotates macroscopically and locks in to Bernal stacking and is indistinguishable from a regular bilayer that was never twisted. So that happens frustratingly often, and we think that it happens in part when the temperature gets too high during processing, but frankly, we haven't really nailed down what causes it and pulled that out of the process. So I would say that maybe 1/3 of the time we get Bernal stacked when we didn't intend it, and then I would say maybe the standard deviation is less than 1/10 of a degree, but we're sometimes off by more than that. For example, we were shooting for 1.1, 1.2 degrees in the sample I'll talk about tomorrow, and we got between 1.3 and 1.4 degrees. And in addition, if you care about two twist angles, the twist angle between the two graphene layers, that's okay, because you can start out, and this was a technique developed by Pablo's group and independently by Emmanuel Tutek's group at UT Austin, what's called the tear and stack technique. You start out with one sheet of graphene, you pick up part of it, then you abruptly pull your stamp off and tear, so that you now have two separate pieces of graphene, but if everything's right, they're still rotationally aligned. You move the first piece of graphene over the second, you rotate by a desired angle, you bring it down and pick up the second, and now you have a controlled angle for the rotation. And so that can be done if you're doing graphene aligned to graphene, but if you want to align to HBN, you can't do that. You have to rely on something like looking at the facets of the boron nitride and looking at that under an optical microscope. That's hard to get precise to better than about 1 degree, and it's even worse than that. You could be off by 30 degrees. So because you can't tell which facet, and there's zigzag and armchair. So there are ways to get more insight into this. We're starting to use Raman, and we didn't invent this, but we're applying Raman to get a sense of how the graphene and boron nitride are aligned. But it's really, yeah, there are lots of ways that it can not work, and it would be great if we could really get more control.
Are
I
there
have a
more?
question if there are no more from.
Yeah.
So,
So-
okay. So I'm actually quite intrigued about the when you show the hysteresis loop shows plenty of tiny steps or plateaus that you attributed to the existence of some kind of domains. Do you have any more insight into, I don't know, the size of those domains or what defines them? Are they defined by maybe defects or wrinkles in the sample, or they are more like the ferromagnetic domains, not that respond to certain size?
Yeah, so those are all excellent questions, Reyes. And I have to say, my first answer is we don't know. But I can do a little better than that. First of all, we strongly suspect that the size of the domains is on the order of a micron, because that's the size of our Hall bar, and you can see that there are some really big jumps in the Hall resistance signal, and those would only happen if if you think about edge states of quantum Hall going around the periphery of a domain. You're only going to get a big change in the signal if that domain basically ends up giving you a path that spans from one edge of the sample to the other. So in an ideal world, we would get, it would always be, h over e squared or minus h over e squared. Instead, we have some dissipative transports present, and I know you're familiar with these sorts of situations in systems with edge states. So first of all, from our work, I would say they're on the order of a micron in size. We don't know what pins them. There is some more beautiful information from Andrea Young's group, because they've done scanning squid with a very tiny sensor to map out the magnetization patterns. I need to look back at that, but I think that there too, that's sort of the size scale of the domains. But I think because we only have 2 samples in the world, however carefully we study them, I don't think we're going to fully know what's pinning them and determining the locations. But I believe that we're going to be soon in a place where we can do more of that and really control it and test those questions.
Okay, thank you.
Are there more questions? Okay.
So if there aren't, let me just, to give you a sense for tomorrow, I'm going to talk about, again, an attempt to reproduce this work that failed, but on the other hand, succeeded in showing us something new and beautiful and puzzling. So it took a long time to figure out what we were seeing. So I'll tell you, I'll step you through the strange behavior that we saw, and the thinking process of trying to figure out what was going on, and then I'll also try to say something about how we hope to get greater control of these sorts of the sorts of things that we're finding are important tuning parameters in the system as we go forward. So moving away from the paradigm of Scotch tape peeling from individual graphite crystals. So I'll hope to engage with some of you tomorrow, and also I invite you in the meantime to ask me questions or to start discussion on the Slack channel associated with my name. And I haven't been trying to track that during the talk, but I will look at it now.
Okay, thank you, David. And I think we can close the session now, and see you all tomorrow. Bye-bye.